We have plus 45 t, and then c is going to be plus 5. Whoa, I wrote a c there. That should be a 5, not a c. Okay, well, now we have our position function. I'm going to go ahead and graph this, and we get quite a bit of information from the graph. Now remember, this was a ball that was thrown straight upward. Now this is the graph of that. It's time on the on this axis here. Remember, this represents time, and then this axis represents height. So this is where the ball was actually initially released. At time 0, um, we were 5 feet off the actually surface of the ground here. Well, we can get some interesting stuff from this graph. For example, this would be the maximum height that the ball actually reached. So at 1.41 seconds, the height of the ball was 36 feet, 0.64. By looking down here where time is 2.92, you can see that the height is 0. So it took 2.92 seconds for the ball to travel upward, starting at 5 feet above the ground, for the ball to go all the way up and then come all the way down and hit the ground. It took 2.92 seconds, and of course we can show this by just by the position. Now that we've constructed the position function, we could get these numbers. So remember how to find the max. You would just take the derivative of this. H prime of t is equal to negative 32 t plus 45, taking the derivative, setting it equal to 0, and solving for t. So we'd have negative 45 over negative 32, and that's going to be equal to your t, and then that should be equal to the number that we saw on the graph at the maximum height, which is approximately 1.41 seconds. Now, if we wanted to find where the ball actually went up and then came down, that's when the height is 0. When the height is 0, so you would take this, set it equal to 0, and then solve for t. And I think we saw what that value was on the graph. But if you wanted to find the actual, how long it actually took the ball to come up and then come all the way down and hit the ground, right? You would set the whole thing equal to 0. That's when the height is 0. We want to know what is the time, right? What is the time? So you'll want to solve for this. Probably going to have to use the quadratic equation, maybe. I don't know. I'll let you do that. And you should come up with what was on our graph, and that was 2.92. So your solution is probably going to be, one of your solutions will be that number there. Looks like negative 0.11, and then the other solution will be 2.92, and of course that's the solution that we want. And of course we need to keep in mind now that this was that this ball, or whatever this thing is, projectile, started at 5 feet above the ground. So we want to keep that in mind. And then it traveled upward and then came directly straight down. Okay, came directly straight down. And it actually turns out, I remember when I was first learning this, I was so excited about this. It turns out that this stuff is pretty accurate. We're not traveling very far distances, so therefore air resistance is kind of really um, doesn't really make a difference. But this stuff's pretty accurate, and you could test this by getting up at the top of a bridge and dropping the ball and seeing how long it takes, let's say, to hit the water or whatever, drop a rock, see how long it takes to hit the water. But you would use this exact same method in doing so. So it's pretty fun to experiment with this.